Since physical things can go wrong, we're going to have some error checking on these link layer frames, just like we had checksums on the transport layer segment and network layer packets. At the link layer, we're going to have a kind of checksum, but this one is called a CRC, for cyclic redundancy check. And the reason we use something different here is because the kinds of things that go wrong between the physical layer and the link layer are a little bit different than the ones we expect at the upper layers. Because we're getting so close to the bottom of the stack here, you might think we want something especially simple and fast to compute. And indeed, a lot of early things use the simplest possible check, which is a parity check. A parity check is a sum of one bit at a time, and when you add up all the bits, then you discard everything but the low bit. In other words, it tells you whether you have an even or an odd number of ones. So here we have an odd number of ones, so we end up with 1. Here we have an even number of ones, so we end up with 0. And here again we have an odd number of ones, so we get 1. So a parity check is a fine sanity check if you expect at most one bit flip along the way. In many media, however, it turns out to be common that corruption is bursty, so that multiple bits in a row are likely to be corrupted. And so if we get 2 bit flips instead of 1 in a row, that will turn out not to change our parity, because we won't change the evenness or oddness of how many ones that we have. If it's bursty at an odd number of bits, you would detect it, but for any even number of bits getting flipped in a row, we won't detect it. We saw that a checksum is a reasonable thing to use at the transport and network layers, and it is less susceptible to these burstiness problems. For example, if we have all of these numbers in our message and we add them up to some total and forget about the higher bits of that total, and we have a bursty change to our number, then we'll get a different number here at the checksum. This is better, but it still doesn't catch all the kinds of things that can happen in a realistic media. Often the thing that goes wrong is a kind of regular pattern where bits get flipped, and if that happens to line up with how many bits are adding up at the same time, then again you will not detect it. And it turns out in the link to physical transition, it's worth spending some effort to do better than this. The key to better checking is getting more mixing among the bits that may or may not have gotten flipped. And an operation that's good at mixing those bits is division. So here I'm showing long division, where I've got some number divided by 43. And you know that this is tedious to do, and part of it is that you keep accumulating information as you go, and you have to do it step by step to get to this final answer. Division can be used for the kind of problem that we want, because if we just consider the remainder and ignore the actual thing that we get by dividing, then that remainder is always less than this divisor. So if we want to checksum up to the size of this number, division will get us the right kind of number. And it has this good mixing property where if I flip one bit here in the middle of my decimal number, change the 4 to a 5, then that effect will bubble all the way through in some relatively complicated way, changing both my division result, but what we care about here, changing the remainder that we might use as a checksum. And if you flip another bit here, it will also propagate, but in a complicated way that's unlikely to get us just right back to 5. Just like long division is kind of painful for people, the division operator is also, in general, expensive on your CPU. But if we pick our numbers just right, we can make a specialized division that is easy to make fast, especially if we're making custom hardware like an Ethernet card. This is the idea behind a cyclic redundancy check. So the formula that we use involves a division. We take the bits that we wanted to check. D is some little d number of bits, so the total size of the frame, say. We're going to get r bits of data, and we just make sure we have r zeros at the bottom of our number, and then we divide by g. G is going to be a fixed number that we always use, like the 43 that was in the previous slide, but for something like Ethernet frames, G is going to be this hexadecimal number here. So we pick G once and for all, and we make hardware that's specialized to that G, and it turns out it can be computed quickly. Still, it's a division-based operator where we're looking at the remainder, and so we get good mixing of the bits to detect correction. It's not that hard to synthesize bits if you are trying to fool someone and give them the same R back for a different D, but for the kinds of corruption that happen on typical media, this is a good way to check for corruption. In fact, it's guaranteed to detect any R-bit error burst. So if your error comes in a burst, flipping bits, or making all the bits 0, making all the bits 1, up to this number R that we've picked, and 32 is a typical thing for Ethernet, then it will detect that error.